Hello everyone, welcome to my presentation. My name is Sihuan Li, and I'm a computer science PhD student at UC Riverside. Today, I'm gonna present a collaboration paper with Argonne National Laboratory, and the title is Towards End-to-End SDC Detection for HPC Applications Equipped with Lossy Compression. So there are mainly two facts to motivate our work. The first fact is that SDC detection is very important for large-scale HPC applications. And to do that, there are already many data analytic-based fault-tolerant solutions proposed. Most of the solutions will assume the smoothness of the data and then being able to detect the SDC if the smoothness of the data does not hold anymore. Another fact is that the lossy compressors have been used for many HPC applications. And for example, the lossy compressors have been used to cosmology simulations including HAC and NICS, weather simulations including CSM and Hurricane, chemistry simulations including EXALT. However, we found that there is no work to investigate the SDC detection after the lossy compression is used. And it's now known how the lossy compression will impact the detection. So our paper aims to fill the gap by making the first end-to-end SDC detection for HPC applications with lossy compression. When we refer to lossy compressor in this paper, we mean the error-bounded lossy compressors. As the name says, the decompressed data will not be exactly the original data, but the difference could be bounded by the user-defined error bound. Take the simple input as an example. The compressor takes the input and the error bound 0.1 as arguments and then compress the data to get the compressed file, which will be usually much smaller than the original data in terms of file size. Then when we need the data, we decompress the compressed file and get the decompressed data, whose difference with the original data will be bounded by 0.1. Now let's clarify what is end-to-end detection and why we need end-to-end detection. So end-to-end detection means the SDC detection should cover all the procedures of the whole execution, including simulation, lossy compression, and data writing. Why we need end-to-end is because not only the simulation, lossy compression, and data writing could also take a significant amount of time. Thus, they have the chance to experience SDCs. The figure below shows the time breakdown of the parallel flash simulation. We can see that at the scale of 512 cores, compression time could be half of the simulation time, and the data writing time could be 10% of the simulation time. With the increasing scale, for example, at around 4K cores, the data writing time could be even more because of the saturated parallel I/O. So we think it's necessary to consider SDC detection for those two procedures as well. So the paper mainly makes the following three contributions. Based on an existing detector, which is 8, it proposes 3 end-to-end SDC detections, taking the lossy compression into account. Then we analyzed the pros and cons of the three solutions. Last but not the least, we conducted thorough experiments with 4 real scientific datasets and 2 popular lossy compressors to evaluate the performance overheads and the detection accuracy of our proposed solutions. To better understand our proposed solution, we think it's necessary to know the existing work first. So 8 is one of the data analytic-based SDC detectors. And the main idea of it is it predicts the value of the current iteration based on a couple of previous iterations. If the difference between the predicted value and the calculated value is beyond some threshold, SDC will be detected. The figure shows what the whole workflow looks like. Suppose at iteration I, SDC detection is needed. It will generate predicted data P and then compare with simulation data S. If the check passes, simulation data will be written to the storage, and the next iteration will start. If the check does not pass, the SDC will be reported. So this figure shows the design of our proposed end-to-end SDC detection solutions after the lossy compression is incorporated. Solution A is based on the existing work where H will only detect SDC in simulation data. Then it adds the SDC detection for lossy compression data writing by reading the compressed file and then getting decompressed data to compare with the original data to see that whether the difference is within the error bound or not. If the difference is not within the error bound, then that means the SDC happened during the compression or data writing procedures. Solution B will make direct comparison between its predicted data and the decompressed data, but then it will also use the checksum to make sure there is no memory error struck the simulation data during the compression and the data writing procedures. In solution C, it will just use the decompressed data as its history to do prediction, and then it compares the predicted data with the decompressed data of the current simulation of the current iteration. Then we take a closer look at the differences of the three proposed solutions. So this page shows whether the 8 predicted data and the data to be compared with the predicted data have been impacted by the lossy compression, by the compression error. Since only in solution C, 8 uses the decompressed data as the history to do prediction. Only the predicted data of solution C will be impacted by compression error. 8 predicted data of solution A and B will not be impacted by compression error. As for the data to be compared with the predicted data, solution B and C will be both impacted by compression error because they use the decompressed data of the simulation, while A uses the original simulation data to compare with 8 predicted data. Intuitively, more compression error should imply less accuracy of the SDC detection solutions. The next difference we want to look at is the time complexity of the detection solutions. So in solution A, the detector needs to scan the data twice. One pass is to compare the 8 predicted data with simulation data, and the other is to compare the simulation data with the decompressed data. In solution B, we just need one pass to compare the predicted data with decompressed data, but we also need to scan the simulation data twice to do memory error detection with checksums, which brings the total number of passes to be 3. In solution C, there is only one pass to do comparison between 8 predicted data and the decompressed data of the current iteration, so the number of passes will be just 1. Lastly, we study if the proposed solutions will work on different I/O modes, including synchronized I/O and asynchronous I/O. The figure shows the parallel simulation with synchronized I/O. The subfigure on the left shows the situation without compression, and the one on the right shows the situation with lossy compression. In the synchronized I/O mode, the next iteration will only start after the lossy compression and the data writing procedure finish. Thus, all the three solutions can work in this mode. However, in the asynchronous I/O, things got more complicated. Looking at the subfigure A, we can see the next simulation iteration can start right after the current iteration finishes, and another rank will take care of the data writing task. Thus, the data writing task and the simulation can be overlapped. Solution A will not work in this mode because it compares the decompressed data with the original simulation data, which requires the starting of the next simulation iteration after the data writing finishes. Solution B will not work in this mode either because it has to wait until the decompressed data is calculated to check the memory error in the simulation data. However, we found that the solution C can work in this asynchronous I/O mode. This is because in this solution, only the decompressed data is needed to do SDC detection, and no original simulation data is required. This means the next simulation iteration can start right after the current iteration finishes. Okay, now let's see some of the experimental results of our proposed solutions. So this table shows the simulation datasets we choose to do our experiments. We choose a CDOV application from Flash and a Vertex application from the NEC5K. Both of these two applications are for computational fluid dynamics. Then we choose EXALT simulation in the field of computational chemistry and the CSM in the field of climate simulation. We use two of the most popular lossy compressors, SZ and ZFP, both in their absolute error bound mode. As for the baseline, since 8 has already been used for SDC detection in HPC simulations without lossy compression, and the lossy compressors are also available to be used for those applications. We set the baseline to be 8 plus lossy compressor, but without end-to-end detection coverage. This means only the original simulation data and is protected, but lossy compression and data writing procedures are not protected. We first evaluate the runtime overhead of our proposed solutions in sequential execution with single thread. The figure shows the performance overhead with different error bounds on the CSM data. The left figure is using SZ compressor, and the right one is using ZFP compressor. You can see that the performance overhead of all the three solutions are under 10%, no matter it is using SZ or ZFP. And from solution A to solution B to solution C, the overheads trend to decrease. The performance overheads on the other three datasets are also under 10%, so we didn't leave them all in the slides. Then we evaluate the detection accuracy of the three solutions. We use the false positive rates to indicate the detection accuracy. The false positive rate is calculated with the number of false positive iterations over the total number of iterations when there is no error injected. Since solution A is not impacted by the compression error, it can represent the false positive rate results of the baseline. And a smaller false positive rate means better detection accuracy. We show all the false positive rate figures on all the 4 datasets. Recall that solution B and solution C will be impacted by the lossy compression error. So with the increasing compression error bounds, we can see the false positive rate also increases for solution B and C. This observation tells us that depending on the simulation datasets, we need to be careful to choose a proper error bound that is not too large to let the false positive rate being too large. For example, if we use SC and solution B to detect SDC in flash dataset, an error bound that is greater than 0.01 will make the detector not usable because of the false positive rate is too large. Another interesting fact that we observe from the figure is that the false positive rate of solution B increases generally faster than solution C, especially on exalt data. We think the reason is that the 8 increases the confidence radius because it uses decompressed data as the history to tolerate more compression error. Besides the performance overhead and detection accuracy, we also care about the compression ratios we can get. This table shows the compression ratios of SC and ZFP on CSM data with different error bounds. What we can get from the table is that with comparable SDC detection accuracy, SC generally has better compression ratios than ZFP. This is because ZFP tends to over-preserve the error bounds, while SC does not. This finding is applied to CSM, Flash, and Exalt dataset, but not the NEC5K dataset, where ZFP compressor has better compression ratios than SD. So finally, we evaluate the performance overheads and the scalability of our proposed solutions. We choose the CSM data and set the error bound to be 0.05 for SC and 1 for ZFP, so that they have comparable false positive rate. The scale is up to 1,024 cores. We found that the overheads are all within 8%, and the proposed solutions scale as well as the baseline. We hope our work can inspire people by presenting the takeaway that low overhead end-to-end SDC detection for HPC applications with lossy compression is promising, but depending on the simulation applications, we should choose the error bounds carefully so that the detection accuracy won't decrease much. Because the detection accuracy depends on the application and error bounds, we want to investigate more different simulation applications in the future. Thank you a lot for listening to my talk, and I'm glad to take some questions from you.